Good morning, good afternoon, and good evening to all the people who have registered and attending this webinar today. I believe we've got quite a few number of people online now, so without further ado, we're going to get started. So I'd like to say thank you and welcome to this webinar that we're giving on augmented vision systems. So we're going to be talking to you for the next hour or so, talking about augmented vision systems, the what, why, and how, and the integration of these. Just as a summary, this is part one of a two-part webinar series. So obviously, if there's anything in this webinar that you see today, please feel free to register for the second part. We'll be looking into more technical details regarding all the vision systems we're talking about today. So just a little background here for how this webinar is going to run. We're aiming to be working and presenting here for about 1 hour, available for longer for questions. We will be answering questions at the end. We've highly recommend and ask, feel free to actually ask questions. In the WebEx session, there's a little chat window with an icon with a kind of speech bubble in there. You can use this to enter questions as the webinar's going along, and we'll try and attempt to answer as many as we can as we go along at the end, I mean. We would appreciate when you leave the meeting, there's a small survey to kind of give some feedback and comments on this webinar, kind of give us some kind of pointers on if it was useful or if you'd like to see more of these. So moving on, what we're going to talk about today is an introduction to augmented vision systems. So we're going to look at what they are, what the terminology is, why we might want to use these within an avionics system, and how we can go about implementing these and what's available to do that. As I mentioned before, today is an introduction to this. There will be a follow-up with more technical details, but today is to kind of introduce the concepts, the details of kind of what they are, why we might want to use them, and how they can be implemented. So we're going to go through, talk about the types, usages, and then we're going to look at the actual system technology, the sensor, hardware, and standards, and then take a series of questions at the end for all of this. So the question is, who's presenting to you today? I'd like to actually just kind of give a little background here. So Matt Jackson, I'm Technical Product Manager at Prestigious. I've actually been involved in embedded hardware and software development for over 20 years, specializing in HMI systems and real-time graphics, working with touchscreens and kind of ARINC 661, and have done augmented vision system concept development in the past. What I'd like to do is actually introduce my fellow presenter, Lucas.
Thank you very much, Matt. So my name is Lucas Friesek. I'm a field application engineer with Core AVI. Been working with Core AVI for about 5 years now, and I have a lot of experience doing safety critical graphics and compute with modern graphics hardware. And I'm going to be happy to be talking about that during this presentation. I will hand it back to you now, Matt.
Thanks, Lucas. So now you know who we are. What we'd like to do is just take you through kind of an introduction to augmented vision systems. So this is actually trying to get an understanding of what the terminology is and what the types of augmented vision systems that are available for us to work with. So I'm going to go through, look at the vision systems, look at why and the usage of these augmented vision systems, why we want them, and then kind of touch on the deployment challenges behind these augmented vision systems in use of aerospace systems. So we can actually break down kind of to a high level description of the type of vision systems into kind of 3 areas here: augmented reality, virtual reality, and computer vision. And what I'm going to do is just kind of step through what each one of these means, some of the terminology behind them, and what they actually do. So we are probably familiar with some of these things, and we see them around. You see them in technology, you see them on the TV and the movies and things like that. And augmented reality is a word that's used frequently. But what it actually means in this particular case is augmented reality is we're trying to present data in the line of view of the user, be that the kind of wearer of the glasses in this particular example, the kind of cockpit. And the idea is we're presenting information. It may be task orientated. So whatever the steps you're proceeding to go through at the moment, it may be just number of text messages, you've got an action you need to do, or it could be contextual. Hey, there's a distance away from your turning or something like that. You're moving along, there's a left turn in 100 yards. So a little icon telling you that. And this is kind of effectively overlaid on the user's view of the world in front of them. And this could be transparent glass, set of glasses, it could be some other method, or it can be a sensor view on a computer generated screen, overlaid with data on top of that. And typically what we're talking about here in this type of augmented reality is a 2D representation superimposed on top of what the scene you're viewing. Now, the kind of one that you hear about a lot in the press, in the TV, you see in the movies and the video games and this sort of thing, is the kind of 3D augmented reality. Now, quite often this is referred to as a kind of mixed reality. And the kind of concept of a mixed reality is we're generating computer generated graphics and positioning them in 3D space. And effectively, we're clamping them, we're referencing them into that 3D space, and adding content to the real world so that you believe it really exists. So in this particular example, we have an iPhone and we put Pikachu on the sidewalk on the pavement. And if we move the actual phone and we move it to point to the trees or we point somewhere else, we won't see that character. But as we move back, that character still appears in the same place. We can walk towards that character, we can move away. And as we do that, the kind of size of that object changes correctly with the right 3D perception. And the idea is we're adding content to the real world as if it was there. So the computer's generated it, and to all intents purpose, it exists. But you just can't physically touch it. And what it's doing is manipulating the real world. So we can then do things like add virtual barriers, buildings, people, or characters in this particular case. So as I mentioned, two types of augmented reality, the kind of 2D flat representation superimposed on what you see, and the 3D augmented reality where we're actually interacting with depth perception within that visual scene. So moving on from the augmented reality, this is a kind of term that people are very, very familiar with and hear it all the time, but virtual reality. And when we're talking about virtual reality, what this is typically trying to do a reconstruction of world data, world scene using data. It may be a made up scene like you get in a video game, or you're actually recreating the world around us using data points and then using a computer to render that view. So it's not necessarily a camera, it's actually the computer generating the actual visuals you see outside. So in this example, we actually have an aircraft here, but it's not real. It's made up of a series of polygons, and it's being rendered in space, and the terrain behind it is not real. It's computer generated with textures and kind of polygon maps all over it. Now, this 3D data may be kind of pre-processed data that's been recorded offline and being actually stored on a storage mechanism and then being plotted, or it could be 3D data that's actually being reconstructed in real time from live sensors, LiDAR or other. The kind of reconstruction of live data is actually quite complicated, and we'll touch on that later, because actually to do this in real time and the kind of volume of information takes a lot of computing power. Now, often this is kind of referred to as synthetic vision when we use this in aircraft display. So again, it's a term that is familiar, and actually virtual reality, synthetic vision, there's a big overlap, and we're talking about the computer generated worlds here and terrain and objects in space. So there's a kind of third category when we're talking about augmented vision systems, and this kind of comes under computer vision. The augmented reality and the virtual reality, we're actually drawing and plotting data for a human to see and to interact with and use that data to actually do a task. Computer vision actually is dealing with how a computer can understand information from an image or a set of sensors. So it's actually doing some form of interpretation as if it was a human and then processing it and doing something with it. So computer vision is a special case. It's not actually kind of drawing something to the screen. It's actually taking data and processing it and giving the computer the kind of ability to recognize relevant information for later use in the system. So in this particular case, there's a kind of scene, it's a kind of night vision scene here, and it can suddenly start tracking objects on the ground and looking at them and trying to decode and make decisions about what type of things those are, and generating data and information to be used later on. So as it processes the scene, what it's doing, if it's vehicles on the ground, it can be tagging them, looking at identification, looking at the velocity, looking at the direction of motion, what type of vehicle it is, what type of aircraft, that type of thing. Now, this data is often then used to support the display of the information to the end user, or to control that display of data. Is it relevant? Do we need to present this? Can I process what I'm seeing as a computer vision to actually extract data that's relevant to the user who's sitting in the cockpit? Yeah. So if we kind of introduce the kind of concepts here and the kind of terminology between the augmented vision, the kind of introduction to all of this is, why do we want it? What's its usage? What's its purpose? What's its value? So
I'm just going to continue from where Matt was. As he was mentioning, these heads-up display solutions where we have augmented reality do exist into the aircraft today. There is known research showing that they reduce the burden of pilots, giving them the necessary information at an arm's length so that they can more efficiently operate the vehicle. More efficiently operate the aircraft. And typically these heads-up display solutions are fixed in what they're displaying. So for example, you looking on this slide, you can see that there's the altimeter information, there's speed information, heading information. This is all fixed. It doesn't matter where the pilot is looking. The information will still be relevant. It's not highlighting specific stuff in the view or doing any kind of tracking on what the pilot is looking at. And so when we're talking about augmented reality, there's a couple of different things. And I mentioned this a little bit just in what I said before. You can have a heads-up display, a heads-down display, and a helmet display. With a heads-up display, you might have just fixed information you want to show, or the information can change based on how the pilot's looking at it, where you have to now take into account head tracking. On a heads-down display, the monitor is fixed in what it's displaying, and you can't actually, or you're not required to do any kind of head tracking on what the pilot's looking at, since the actual display is fixed in its position. And then with a helmet display, it's very important to do this kind of tracking, since wherever the pilot looks, the helmet's going to move with the pilot's head, and you'll need to show the relevant information for where the pilot is actually looking right now. And when you start to look at this with a heads down display, you'll have some kind of input information and you'll be projecting your flat 2D image on top of it. With a heads up display, you'll have the information projected onto glass where you might want to do tracking or you might not need to. And then with the heads up, the helmet display, wherever the pilot's head is moving, that details need to be tracked now. So this goes into more of the advanced vision topics that we've brought up in the presentation. With helmet-based displays, we need to start tracking 2D information in the scene to know, is what we're highlighting relevant? Are we actually mapping it correctly to what the pilot is looking at right now? If the pilot turns his head, is there different information we need to display in order for it to be more relevant to what the pilot is currently doing? And these advanced vision systems allow us to change content based on what the head is looking at and have a more efficient display for the pilot and reduce the cognitive burden for the pilot based on selectively showing information and not overloading the pilot with extra information. The other issue that comes up when we're talking about augmented reality is adding things to reality. So it's not as straightforward as, you want to put a flight path on top of what the pilot is looking at. In the real world, there's additional details such as the depth of the scene that we're looking at. And so if you draw a straight flight plan between points, it might not be accurate. So if there's a mountain in the way or there's some kind of vertical terrain, then the straight line that we draw could intercept with the mountain and it won't be an accurate display. So we have to start taking into account a real model of the world. So we need information about the world around us. When we're adding to reality, we might want to also highlight threat zones or special areas, landing corridors, that type of thing in reality. And these are, again, places where we need to take in a full 3D representation of the world into account. And so when we're talking about advanced vision and doing this kind of tracking and positional information, an interesting topic is landing corridors, where we begin to highlight a path that a pilot needs to fly in, and so that we can reduce the cognitive burden of the pilot by letting them know that if they want to reach this certain position, they just need to fly through this highlighted region. And as the pilot moves around or moves his head, the actual highlighted landing corridor will move around and follow where the pilot is looking so that it's accurately representing what the pilot needs to do. So now I'm going to move over to virtual reality. And this is something that's especially important when we talk about degraded visual environments, where if you're using vision-based sensors like LiDAR or camera or IR, it's not necessarily giving you the detailed information that you need to operate the vehicle efficiently. So a classic example of this is a helicopter landing in the desert. As the helicopter goes down, the rotors of the helicopter begin to pick up the dust in the desert and cloud the vision of the pilot. This is a case where having virtual reality is especially useful. If you have a model of the world around you that's preloaded or that you're able to capture through more advanced sensors, you can actually display that virtual model to the pilot instead of what's really there in the scene. And so the pilot can view where they need to land completely unobstructed. And the point we really want to get to with this is that each one of these solutions are very powerful, but when combined together, this is how we can actually build advanced vision systems. So we can gather real information about the scene, augment the reality that we're looking at, and then pull in virtual reality data when needed. And this is how we can go about really building an advanced vision system. And another thing that comes up with this is that if we just capture this data as is and we try to present it to the pilot, it's noisy, it's distracting. You can see on this video here, I'm sure as I'm talking right now, it's kind of distracting. It's taking a lot of your focus away and it's not absolutely clear what you should be focusing on here. And so this kind of mixing of the data and highlighting what's important and focusing what we want to deliver to the pilot is really key so that we don't overload the pilot and make operating the aircraft more dangerous. And so here's some examples of, again, combining all of these systems together. So the last thing I want to talk about here is the deployment challenges related to advanced vision and augmented vision systems. And one thing I want to focus on here is that AR and VR have been around for a long time. So you might think, oh, you know, they've really been kicking off right now. If you look around in the commercial world, the augmented vision on cell phones like the iPhone is really popular, and the virtual reality like Oculus headsets and HTC Vive headsets are super popular, but they've really been around for a long time. Ivan Sutherland has been a key player in the human machine interface world for a long time, since back in the late, I believe, 1970s and 80s. And he was actually working on AR and VR solutions back then. Of course, as you can see in the pictures here, the setup required a lot of equipment, and it wouldn't be ideal to fly in an aircraft, but this was something that was being set up in the 60s. And when we're talking about virtual reality and having true solid 3D geometry, this again has been something that has been done since the 80s. So this is not groundbreaking technology necessarily, but being able to use it in an aircraft is more groundbreaking because the computation power here is significant. When we're looking at those legacy AR and VR solutions, they needed supercomputers, they needed large equipment to support it. And for example, very early augmented reality solutions in cockpits relied on heavy workstations like the SG Ionics, which were, you know, a 90 kilogram, 200-pound machine, which you can only fit in a special type of aircraft that can support that. It drew tons of power, so it wasn't ideal for typical avionics use cases. The other, you know, downfall of these workstation systems is they're meant to sit on a desk or in a server room. You know, if you whack it too hard, cards are going to fall out of place. It's not ruggedized. It's not really meant to go into an aircraft. And so these are a big limitation when it comes to trying to use all these things that the commercial world has been using to build HMI solutions. Now I'm going to jump to my portion of the presentation. And on my portion of the presentation, I'm going to be focusing more on the how here. And before I jump right into the how, I'm just going to talk about why haven't we seen advanced vision systems in the cockpit today? And you know, some of you might think that the work that's going on right now is advanced vision systems, but I really want to focus on taking things to the next level. You know, doing real-time capturing of LiDAR data, 3D point clouds, processing multiple gigabytes of data to build real-time accurate models of the world around us so that we can properly augment the vision systems that we're using. And so what are the existing problems in advanced vision systems, or really in the technology that we've been using in the past that are preventing this type of application? First off, sensors have not typically been accurate enough, or the accurate versions were too expensive, or they consumed too much power, or they took up too much space. The volume of data that you needed to process was far too large. For example, LiDAR data is being used today in aircraft, but since the volume of data is so high, typically an aircraft will go ahead of time, capture the LiDAR data, bring it to a supercomputer that's going to pre-process the data, and then the pre-processed data will be loaded onto aircraft to use. So it's not real time, it has to be pre-captured and pre-processed. The other thing is being unable to utilize the hardware that you want. So many people are working on prototype solutions where they have these pre-processing solutions that take advantage of hardware like NVIDIA using their CUDA technology, which does not have a path to certification for DO17A and DO254. And so this leads to my next point, is that these systems existed, but there wasn't a path to certification. So there was no way to either certify the hardware or certify the software that you were using on those systems. And so these have, in the past, typically been the problems for building advanced vision systems. And so what's different today that would allow us to do that? Well, There's advanced sensor technology that can provide more detail, more resolution in smaller spaces using smaller power or smaller amounts of power. Modern hardware that supports highly parallel computation that is available in ruggedized form factors that does have DO-254 certification, and then does have software support for DO-178 certification. And there's modern standards that mean you don't need to build everything from scratch. The standards simplify the certification process. So all of these things are working together today to make building advanced vision systems a reality. So I'm first going to talk about sensor technology. I'm going to go over what kind of sensor technology is interesting to us from an advanced vision systems perspective. And when we're talking about advanced vision systems, we're typically talking about building an accurate model of the world around us in real time, and also being able to detect and track objects in the scene that are interesting or valuable to whatever the mission is. And when we're talking about these types of information, there's two key sensor types that are interesting to us. There's image-based sensors that are capturing a 2D model of the world, and there's LiDAR or kind of radar-based systems that are taking a 3D representation of the world, or capturing a more 3D representation of the world that we can use. So first to start, image sensors, what are they? These are camera type sensors that are capturing 2D visual data. So we have an X and Y component of the data around us. And then it has either light, thermal, or some kind of EM-based data that it's capturing for each X and Y position that we have. The nice thing about image sensors is that they are able to provide areas of interest, object detection, and classification for us. They fit really nicely into standards that or technologies that work on those types of problems. And in the standards section, I'll touch on this a little bit more. And this is something that we'll dive more into in part 2 of this webinar. But one thing is they're not really great for accurately modeling the world around us. They don't provide depth information. We're only getting a 2D representation. And there's things I'll say, quote unquote, hacks that you can do with 2D image sensors in order to get more positional information, such as depth, where you're using stereoscopic vision, or you have multiple sensors and you're using that to try to capture more of a 3D representation of the world. But this is trying to make 2D sensors try to do something that they weren't originally designed for, where there's other types of sensors that can provide more detailed information for us that fits this need. And so what are these other types of sensors? Well, there is LiDAR. So these are sensors for capturing 3D positional data of the world around us. And like the image sensors, you're capturing some wavelength of light. So you can get information about color, thermal data, that kind of thing. But the real key thing is getting this XYZ 3D positional data so we can have an accurate model of the world around us, and then we can reproject that model so we can look around in different perspectives or do any kind of processing where the center of focus is not necessarily the aircraft itself or where the sensor is mounted. And again, what can they be used for? Building a full model of the world, gathering the depth information, positioning ourselves in the world, or positioning other objects in the world. One very big drawback when it comes to these types of sensors is that the data they capture, these point clouds, are extremely large. And when I say extremely large, I'm talking like a single capture can be in the gigabyte range of data. And if you're trying to do real-time capturing, you're looking to capture, 30, 40, 50, 60 times a second, depending on your latency requirements. And so you start getting into the tens to even hundreds of gigabytes per second of data processing that you need to do if you wanted to process LiDAR information in real time. So let's talk about a little bit on modern hardware. So what is modern hardware doing right now to assist us with this problem if we want to, for example, process LiDAR data in real time? Well, one of the big benefits of modern hardware is that it's no longer a 200-pound supercomputer. So it's available in ruggedized form factors like VPX and XMC, meeting open standards for sensors, that type of thing. And there are options for DO-254 certified hardware available today as well. The other key thing is this modern, graphics hardware has more computation power than ever before. So if we compare this, for example, AMD E9171 to the old SGI Onyx, it's much more capable than that SGI Onyx was in a more desirable package. So when we're talking about these modern GPUs, they can process trillions of math operations per second. They're running at 30 watts or lower of power, and they can fit on these very small, low weight boards that are XMC and VPX form factor. So when we're talking about size, weight, and power, they're checking the boxes for everything we need to fit on modern avionics systems. The other thing, and this is a point I'm going to jump back on a lot of times during this presentation, is that they support simultaneous graphics and compute. And right now, the key benefit to this is, especially when we're talking about large volumes of data, is that on legacy systems, you might have processed the data using a specialized DSP, ASIC, or FPGA, and then when you wanted to visualize the data, you need to move it from this specialized processor like a DSP to the GPU for visualization. So now you have to, if we're talking about a LiDAR point cloud, there could be gigabytes of data there. So now we have to do a gigabyte or more of copying to move the data from the DSP to an area that's accessible by the GPU, that the GPU is able to operate on efficiently. So when we have support for simultaneous graphics and compute, the GPU can do the computation directly in its own memory and then visualize based on that computation, eliminating this kind of double copy and allowing a lower latency since we're not adding time to actually copy the data. So modern hardware, I just want to compare a little bit GPUs to modern CPUs to give you a better idea of the computation power available. So for example, the Intel i9-9600K, which is a very high-end Intel CPU, fairly modern, it supports about 6 gigaflops. And if you're not familiar with a gigaflop, it's basically a billion floating point operations per second. And I'm just going to refer to that as basically 6 billion math operations per second per core on the CPU. And this is when optimized using the special SIMD instruction sets available on x86. And so this is kind of like the best case scenario for performance you could get out of this Intel processor per core. But one thing to keep in mind, and I'm not going to say that this number is measly, it's a very astonishing number. This is much higher than systems in the past have been capable of doing. You can achieve an enormous amount of computation with 6 billion math operations per second. But another thing we have to keep in mind is the CPU is responsible for running the operating system, other applications that might have synchronization requirements or other real-time requirements that prevent this full 6 billion operations per second from being used. And then when you go to compare this against, for example, the AMD E9171 GPU, this GPU is capable of performing 1,200 gigaflops, or I'll reword this as 1.2 trillion math operations per second. And so this is a substantial increase over what is available on the Intel CPU. And I'll caveat this a little bit, okay? The GPU is able to do this when you're working on highly parallel problems. So these are problems where you can operate on individual points of data in parallel independently. And when we're talking about a problem like processing a point cloud, this is exactly what we're trying to do. There's parallel points of data that we need to process individually and independently. And so we can actually achieve this 1.2 trillion math operations per second. The other thing is when we're using a GPU for visualization, there's lots of leftover computation time that we can use to run these other computation tasks. And the GPU isn't being shared to run the operating system and other applications on the system that might have real-time requirements. So it's focused to this task of visualization and data processing. So this full 1.2 trillion operations are available to us. Now let's touch a little bit on modern standards. So what are modern standards doing to help us solve these types of problems? Well, first off, why do we want standards? It's, if you're not familiar with the standards I'm talking about, it might seem a little bit weird to just pull them in, but there's two key points it comes to when using standards that really benefit us when we're building these types of systems. One is to avoid building everything from scratch. A lot of standards that I'm going to talk about today provide library functions to us to implement standard operations so that we don't need specialized implementations to do, for example, matrix math, or specialized implementations to do filters on images or that type of thing. And so now we don't need to build our own implementation or our own proprietary standard to do this type of computation. And the other thing is, since we're relying on these standards and a lot of these standards are meant to be portable, we can keep the systems that we're building portable between different platforms. And if you look at advanced vision systems today, if they're doing this type of processing where they're taking advantage of a specialized ASIC or DSP, those are targeting those specialized processors. They're not designed to be portable. So if we want to move it to another platform, we have to port this custom solution to every single platform. Whereas if we rely on these standards and the other platforms we're targeting also implement these standards, we can more easily move the software that we're building and the systems that we're building for advanced vision across multiple platforms. So when we're talking about scaling advanced vision systems, this is very important. Now, the two standards I really want to focus on for this presentation for advanced vision systems are Vulkan Safety Critical, or Vulkan SC, and then OpenVX, and specifically the safety critical version of OpenVX. And both these standards are developed by the Khronos organization. And if you're not familiar with the Khronos organization, they're a nonprofit group that develops several graphics and compute standards. They've existed for a long time. They originally started developing the OpenGL standard, and some other standards that they've worked on are OpenCL, OpenVX, and Vulkan, which you might be familiar with. If you're doing anything with HMI, you're probably very familiar with OpenGL and its safety critical counterpart, OpenGL SC, or OpenGL Safety Critical. The very interesting thing about Khronos, especially for us when we're talking about avionics applications that have safety requirements, is that Khronos does have a safety critical working group that is focused on developing safety critical variants of their commercial standards. So they have a long-term history of doing this. This is not like some thing that they've adopted recently. They've been doing this for years now, starting with OpenGL Safety Critical and now migrating with Vulkan Safety Critical and then the Safety Critical deployment feature set for OpenVX. So Khronos definitely has the pedigree to develop these safety critical standards when we're talking about graphics and compute applications. Now, what is Vulkan Safety Critical? Well, this is the next generation graphics and compute standard from Khronos. It's based off of the commercial Vulkan standard, which is meant to provide advanced graphics and compute features to modern applications. So if you compare Vulkan SC to OpenGL SC, OpenGL SC was designed and developed targeting GPUs that were built basically in the late 2000s. And so a lot of advanced features that exist in hardware today aren't available in those standards, such as compute shaders, tessellation shaders, object shaders, and they haven't been added to the standard, whereas Vulkan Safety Critical does expose this modern GPU functionality to the application, so we can take better advantage of GPUs that exist today. The other thing, and again, I'm going to keep beating this point, is it allows the GPU to be utilized for simultaneous graphics and compute operations. And again, to focus on that, when we're trying to visualize a large data set like a point cloud in real time, we need to eliminate any kind of latency that might come up with processing this data. And this data transfer operation is expensive. When you're talking about transferring tens of gigabytes per second of data, then you need to be sure that you have as few copies as possible, because one copy already might start hitting bus limitations in the system. And so if you can keep the data local on something that's faster to access than, for example, the PCI Express bus, then you can ensure that you're not adding latency to your system for just copying data, not even processing the data. And this is very, very important when we're talking about low latency real-time processing of things like point clouds. The other thing that comes into play with advanced graphics features is things like tessellation and object shaders. And the idea behind these technologies is that the GPU can actually build up the rendering primitives we want to show itself. So it can build up the points, lines, and triangles that we want to show without having input from the CPU. The CPU can just point it at a data buffer, and then the GPU can go look over that data buffer and build these, for example, triangles that we want to render. So it eliminates any kind of copying between the CPU and GPU to set up these rendering primitives. That really covers what I want to talk about Vulkan Safety Critical. The other standard I'm talking about is OpenVX. And so what is OpenVX? The VX part of it stands for Vision Accelerated, and it's a standard designed for accelerating computer vision applications. It's developed by Khronos. It provides support for a number of features such as classical image filtering operations and advanced neural network features, and it has a safety critical deployment feature set. And I'll go over what these offer to us. If you're interested in how this technology actually works and plays into the advanced vision system, like how would I use the computer vision feature set or the neural network feature set for an advanced vision system, then I would encourage you to attend the second half of this webinar where we'll go into more of the technical details. But first, to start off, what is the vision feature set? It provides classical computer vision operations. So to give you an idea of what some of these are things like filters, convolutions, blur operations, these types of things. The idea with this is that you can do image pre-processing and post-processing so that you can hand it off to another algorithm that can operate only on the important parts of the image, eliminating, processing of more complicated processing of parts of the image that are not of interest to us. The other feature set is the neural network feature set, which provides functionality to build neural networks layer by layer. And it supports several standard activation functions for neural networks. And if you're unsure what any of this means, again, I would encourage you to join the part 2 of this webinar, where we'll go into more detail about what these actually are and how they help us with advanced vision systems. But one of the key interesting things for us is if you're working on any kind of advanced vision system technology where you're doing object tracking, object detection, it's very likely that you're trying to take advantage of a neural network at some point, since these are the state-of-the-art technology for doing object tracking and object detection. And one of the nice things about OpenVX is that it allows you to import neural networks defined in external tools, giving you a path to certification that those other tools don't give you. And what do I mean by this? Well, OpenVX supports this other standard from Khronos called the Neural Network Exchange Format, or NNEF format, and it provides this feature called the import feature set, where you can take a neural network developed in a tool like Caffe or TensorFlow, and these are kind of the industry standard tools for building and training neural networks. And then it allows you to process that neural network, export it to this common exchange format, and then import that into OpenVX, where OpenVX provides a deterministic execution platform where you can be sure about how much memory it's going to take to execute your neural network, how much time it's going to take to actually execute the neural network. So it provides this certifiable deployment platform for a neural network once you've deemed that your neural network is safe from a conceptual standpoint. So that's really what we wanted to talk about for this presentation. So in conclusion, as Matt was talking about at the beginning of the presentation, augmented and advanced vision systems can really improve the cockpit design approach. They can allow pilots to be more efficient in the aircraft and focus on the problems that they need to focus. Modern avionics hardware that is available today better supports these types of systems. They're available meeting size, weight, and power constraints of aircraft today. They have things like DO-254 certification. Modern graphics and compute standards today better facilitate building systems like this, where we don't have to reinvent the wheel, and we can keep the solutions that we build portable across different hardware platforms. And at the end of all this, when we're talking about avionics applications, all of these components are being provided with certification evidence for both the hardware and software, making this a real possibility to build advanced vision systems today. So thank you very much for attending. If you have a question and you haven't submitted it yet, I encourage you to submit it through the question box, as Matt mentioned. If you're interested in receiving a copy of the presentation, please email the email that's available there. And now I will hand it to Paul, who's going to go over the Q&A rules here and give some background about the technical issues that happened during the presentation.
So we apologize for the technical issue. It was a power outage that Matt suffered. He is back now, but I'm not sure whether he's still on battery power or so I'm going to ask the questions, and Lucas and Matt will answer them if they're able to. As Lucas said, you can submit questions through the chat window, and then I'll ask those. So the first question is for Lucas. How do these modern graphics and compute solutions help solve the fixed position problem with augmented vision?
Hey, thank you very much, Paul. That's an interesting question. So when we're talking about the fixed vision or fixed position problem with augmented vision, we really need to start tracking the position of the pilot's head or helmet to know where they're looking. If you attended the previous joint webinar we did with Presagis, we talked about how GPU compute can be utilized to do things like object tracking and head tracking and hand tracking for gestures. The same kind of approach would apply here, where you need to get some kind of sensor data that's showing in space where the helmet is. You can then use that to get an idea of where the head is in relation to the display you want to show on, and then adjust the projection you want to do for the position of the head so that it's actually in line with where the pilot is looking. So this is something that modern graphics and compute solutions help with, since the high volume computation that's available on modern GPU hardware enables more efficient head tracking and body tracking solutions.
Thanks, Lucas. The next question was from somebody. I thought LiDAR was already being used in aircraft today. How is this different?
Okay, so that's again another interesting question. So I mentioned this, I think, very briefly. LiDAR is used in aircraft today. It's not typically used in real time, simply because the data volumes you need to process are too high. Or if it is being used in real time, it's taking advantage of hardware that hasn't been certified or software that hasn't been certified, and it's not being used for the safety critical aspects of the actual aircraft today. So the difference we're really focusing on here in our presentation is doing this real-time processing of high volume data like LiDAR, and then being able to use that in a way that would actually be certifiable.
Okay, thank you. Can OpenVX be used for three-dimensional data?
Okay, so OpenVX, as I mentioned, it provides vision capabilities and neural network capabilities. There's nothing specific of those that they're tied to two-dimensional data. If the algorithm is actually applicable to n-dimensional data, it does provide functionality to do that. And then the neural network implementation it provides is not actually tied to any kind of vision system. It's a generic neural network implementation. So if the neural network you're importing is designed to use three-dimensional data, you can just provide it three-dimensional data. There's no limitation for just using, for example, 2D image sensor data.
Okay. Somebody asked whether there will be a recording of both webinars. I can answer this one. It's my level. There will be a recording of both webinars, so the people who are unable to attend the second one or want to take a re-listen to this one will be able to. And on the screen at the moment is the egmarketing@presagis.com. If you have any problem finding the recording or wanting to get a copy of the slides, please send a message to that address, and either Presagis or Core AVI will respond to you. Lucas, if GPU compute capabilities are used to perform the computations using internal GPU hardware, how is it ensured that the integrity how is the integrity of the GPU hardware ensured?
Hey, this is an interesting question, actually. So, ensuring the integrity of the GPU hardware when you're talking about compute isn't that different than when you're talking about graphics. A lot of the same hardware that is being used for the graphics portion is also being used for the compute portion. So these are like the shader cores that exist within the GPU, these highly parallel processing cores. Core AVI does have a solution for doing GPU hardware monitoring that we call TrueCore, that's submitting known tests to the GPU. And this is kind of our solution to support GPUs that don't have additional hardware functionality for validating the integrity of the hardware. There are some more recent GPUs that have been developed. For example, ARM has recently announced their G78AE GPU IP, which is designed around safety. It does have some more monitoring capabilities built into the hardware itself. And another interesting feature, kind of unrelated to this question, but when we're talking about GPU compute and safety, it is very important. It actually supports hardware partitioning of the GPU. So you can split the GPU into independent cores that are separated from each other than their connection to the main system bus, and they can operate independently. They have their own cache, they have their own command processor, that type of thing.
Thanks, Carlos. I think that's the next question is for Matt. If you can hear me, Matt, and if you can talk. There's a kind of comment and question which says it would be good if simulation would be able to simulate radar range, not only line of sight, but radar equations. Are you able to answer that, Matt?
Sorry, could you just repeat the question there, Paul?
Yeah, the question is about simulation of radar and what's possible. Radar range, not just line of sight, but according to the radar equations.
Okay, that's a fantastic question, actually, Paul, because we've done some of that in the past, actually, in simulation where we do physics-based modeling of radar. So, i.e., what will it see? What's its propagation? What's the reflection from that? Based on a database. So, using a 3D database. I know inside Presagis we actually have tools that do this, where we can actually send out a signal, look at what would happen, but it's using a virtual 3D database to do that. And obviously there's kind of material tagging and things like that, but there's a lot more to it than, as you say, line of sight, because propagation and things like that. There is a lot of computation to do that in real time, but it's the sort of thing that you could apply and say, hey, I've got a virtual reality world. What is the capability, so you don't actually have to switch on your radar? Where could I see without having to do that? So yes, I think the answer is yes, it's possible. It has been done in the simulation world before. It hasn't, as far as I'm aware, been used airborne to actually simulate in the cockpit, but there's nothing with obviously now the compute power available to actually do that in real time.
Thank you. The next question I think is also for you. How can you use LiDAR in aircraft? I heard that LiDAR is limited in distance that it can reach.
And that again is a great question, because yes, there are limitations, and it's applying where do you use LiDAR, what's it for, how far ahead are you looking ahead, what type of thing are you trying to build up. Typically, obviously, a LiDAR kind of thing will generate a huge point cloud. It's typically the intention is not to kind of see off into the distance, kind of very far ranging. It's looking for the more close range towards you. So I think hopefully the video worked. I apologize if it didn't. I wasn't online, but the idea is you can actually do the LiDAR, calculate kind of objects near to you. So as you're coming into land or you've got a brownout situation, it can help assist at that sort of level. Obviously further out, LiDAR can be assisted if you're actually building up your offline database. So as you're recording areas of interest, you can actually build up your offline database using LiDAR, which is typically what a lot of people do today, is use a LiDAR system to actually build up an offline database, which is then used once the aircraft is actually flying to actually have that virtual reality database to do rendering, and then you can then apply in the short range the kind of correlation to make sure that that database matches what your sensors are actually seeing, to ensure that you don't have a kind of a safety problem or a correlation issue of that data being out of date.
Thanks, Matt. I'm not sure who this question is best addressed by, but the question is, for head tracking systems, will you be talking about latency in the next presentation?
I can take that one, Paul. I will be talking about latency in the next presentation. It's one of the challenges to actually implement this effectively, is the kind of throughput latency. There's multiple latency issues that come into it. So we'll be talking about some of those issues and what the kind of causes of them are, and any ways that could be mitigated.
Okay. Somebody wants to know what kind of building blocks are available at Core AVI, so that for this.
Okay, so obviously I can answer that. So Core AVI is, as I mentioned, provides a solution for Vulkan Safety Critical and OpenVX. I would consider these to be building blocks, providing these implementations of open standards. The other thing that Core AVI does have available when we're talking about high volume computation is our compute core solution, which provides basically a generic math acceleration library. So it provides functionality to do n-dimensional linear algebra or basic linear algebra subprograms, and n-dimensional Fourier analysis, fast Fourier transform, all being accelerated by the GPU. One thing I'll touch on here is all these products, we're basically providing you an API that's available to your application, and then we're certifying everything that's running on the GPU, so you don't have to worry about doing code coverage on shaders, for example, or doing the actual object code to source code traceability when we're doing DALE level certification.
Thank you. Similar question, and I'm interpreting a little bit the question here. Is there an actual implementation of Vulkan SC today?
So Vulkan SC is not currently ratified yet. It's in the working group. Kronos announced that it would be ratifying it later this year, so the spec will be publicly available. So it's right now at this time, it's basically impossible to say that you have a Vulkan SC implementation available. I will say that Core AVI has an implementation of the original proposal for Vulkan SC and some of the updates that have been done along the way during the ratification process. It is not Vulkan SC itself, since the standard has not been ratified at this time, but we're very involved in the Safety Critical Working Group. We actually chair the Vulkan Safety Critical group within that. And so we're keeping our implementation up to date with what's being done within the working group, so that when it finally gets ratified, we'll have a conformant implementation to provide. But it is available today. We can give you right now our VK Core SC is what we call it, implementation that is very close to what Vulkan SC will be once it's ratified.
Thank you. This is a slightly complicated question, so listen carefully. Do you know of a real-time sync solution for multi-consumer augmented reality situations where more persons are looking and possibly changing user input? That makes sense.
I think I understand the question. From Core AVI's perspective, I'm not really familiar with the real-time sync solution. Matt, from the HMI perspective, you might have had some dealings with this. Are you familiar with any solutions for multi-user augmented vision?
That's what I'm just trying to kind of ensure I've got the understanding if it's multi-user or multi.
It says multi-consumer, but then refers to multi-users in parentheses.
So there are some concepts that I'm aware of. Have I seen a deployed solution? No, doesn't mean there isn't one, but I think in a multi-user environment, there's a lot of conversation about how would you use this together and what augmented reality would work like in there. I think the kind of closest to the kind of multi-consumer, multi-user type thing is actually in the consumer world, where I know people like Microsoft have got their mixed reality world where you can actually share spaces and things like that. Trying to apply that in the cockpit, I think, is an interesting kind of human factors question of looking at how you would possibly apply that.
Yeah, thank you. The next question is about the next presentation, and it asks, would you be talking about the type of computer vision system like the EVS systems currently in use by Southwest and FedEx in their hubs today? It seems to be more related to computer vision specifically.
So I can answer this a little bit. So I don't think we're specifically going to talk about Southwest Airlines and FedEx, but definitely in the second half of the presentation, we're going to talk about enhanced vision systems currently in use today, and if there's any limitations with them.
All right. Someone asks, is it possible to have these augmented views also for ground personnel simulation, like training of ground-based air defense?
Simple answer, yes. So one of the areas is looking at how do you look at an augmented view from the ground, and specifically if you look at UAV or kind of unmanned aerial vehicles. There's a lot of thought and conversation about, do I fly the aircraft? Do I actually operate from the ground? And what can I also send to operators on the ground to interact either with the pilot or to control the system, and what view and what data would need to be shared between the two? So it's an interesting one because the kind of concept of augmented or virtual reality can minimize the amount of data that has to be sent back to a ground system as well. So in terms of training, yes, it makes a lot of sense for the kind of training world, but also just the ground-based control or visualization of a scenario or a system that's evolving on there.
Thank you. I think this is directed at Lucas. You mentioned some figures, but what are the minimum hardware resources that you'd actually need to run a vision system?
So I think this really comes down to what you want the vision system to do. So if you're talking about real-time processing of like point cloud data, you need a high-end GPU to do that because the volumes of data are just so large. But if we're working from, for example, offline models of the world, then the computation requirements drop down significantly. There's lower power GPUs with lower performance that are capable. I can't really give a general answer to this. It really depends on the specific system you're trying to build, and what are the amounts of data that you're trying to process in that system. I can say, for example, that we do have customers today who are working with the i.MX8 Quad Max. So that's one of the lowest end GPUs that we support today. It's, I think, about 10 times slower than the E9171, and they're using it for some advanced vision systems right now.
Okay, thank you. There is a question here about 6G. What role, if any, 6G might have in the future? Apparently, there was a news item where cloud-based 6G may have 0.1 to 0.01 millisecond latency for massive data. Any potential application to augmented vision systems here?
So I can, I think, answer half this question, and then Matt can provide input how he sees on the other side. So I think when we're talking about getting different types of data sources, I think from different perspectives, this is interesting. But when we're only looking at from the perspective of the aircraft itself, the real bottlenecks here are how quickly can we get data to the device that we're going to use to process it and the device that we're going to use to visualize it. So these are real bottlenecks in systems today that have to be overcome before we can even talk about streaming data to an aircraft using something like 6G.
So yeah, that's an interesting one about what's the usage. So one of the key things about airborne activity is actual data and where does it come from. So a lot of the stuff we've talked about is actually on board the aircraft, and as Lucas says, is processing that data. The moment you kind of can get data links to third kind of party systems, the ability to kind of do other types of processing and stream that data become quite interesting. So in a typical world, we have various bits of information, but currently the data rates for other aircraft and other things going on, the actual data rate that that's being sent at is quite limited. So there's data being sent about other aircraft positions that are beyond your visual range. They're actually coming in at quite a low data rate. So if you were trying to use that in augmented or a VR system, say, per example, pilot wants to look ahead, there is some form of aircraft coming into land and he wants to know how busy the airport is and what the kind of clearance is, and you kind of do a virtual pan to the airport. To get that data updated quickly, you would actually need quite a large volume. So you kind of start getting into the what if of, hey, I've got opportunities here for allowing my VR or my augmented reality to allow me see beyond visual range effectively. So you can actually prepare yourself before you get somewhere if you've got that type of data stream. It kind of gives you a situational awareness. So I know kind of streaming data is very helpful. Obviously, if you can stream large volumes of data, you can actually disperse the processing. So if you've got, I won't go into a particular application that I can say, but there are ways of doing the offload on more than one platform if need be, because you're talking short range possibly between kind of aircraft where you may not even have enough electrical power to run all the computers, but you can offload onto other ones that are nearby, so you can actually start looking at distributing that. So there are kind of conversations that takes work. There are possibilities if you could use this. There are many kind of opportunities if you can increase the bandwidth of data coming across.
Thank you. It seems that in-cockpit cameras could be used to determine pilot head position or orientation in almost real time. Does this make sense? And taking advantage of the new hardware and software, would it be possible to extend this concept to include hand, finger, body tracking for ergonomic analysis?
So this is actually something we talked about in our last joint webinar we did with Presagius. So whoever asked this question, I would encourage you to go check out. I believe this presentation is available on the Core AVI YouTube channel. And I believe Presagis also has either on their website or on YouTube it available as well. So you can go check out that presentation. We do talk about using things like image sensors in the cockpit to do head tracking and hand tracking for more advanced gesture systems in the cockpit. So I would encourage you to watch that webinar. The answer to your question is basically, yes, that does make sense. And we have more detail if you're interested to go check that out.
Yeah, it is available on the Presagis website as well. So either works. And if you have any problem, can't find it, then as I said before, send email to that email address that's listed on your screen right now, and we'll help you out.
Yeah, and if you're interested in that area, there are other things you can use that type of system for. That if you're interested, please feel free to get in contact to Presagis or Core AVI. There are some more interesting use cases, especially when you mention ergonomics, but there's some also other use cases in the cockpit where the use of cameras and tracking by using this hardware make a lot of sense as well, and give you advantages of the type of systems you can interact with and the kind of some human factor issues that come about today that can be resolved by doing that.
Okay. Somebody wants to know where face fits into this and whether these products can work in that kind of environment.
So I can take part of that and take my ARINC 661 hat because part of FACE ARINC 661 is actually part of the graphical subsystem for FACE, and I'm on the ARINC 661 committee, and we've actually introduced recently in Supplement 8 3D map objects. So at the moment that's at a higher level. It's more the it's 3D augmented graphics, so you can actually position in space, and so things like waypoints and route lines and things like that. So it's kind of cross between the VR stroke AR approach there, more probably leaning towards the VR side. That's actually part of Supplement 8. There's ongoing work now in Supplement 9 that would mean that looking at how the terrain and other things interact with that and how that can fit together in the ARINC 661 world for the kind of graphics HMI. So as FACE uses it, we would suspect that FACE would move forward, hopefully, and kind of take on this new functionality that's becoming available in the standard, so that some of these synthetic vision systems or kind of VR type of thing can use standardized objects, widgets from the ARINC committee rather than kind of reinventing it all.
Okay, I think I can take the second half of this question, or at least the Core AVI perspective of this question as well. So currently in the FACE technical standard, the most recent version came out. Well, obviously, Vulkan Safety Critical isn't ratified yet, so it can't be added to the standard. But OpenVX did not have its safety critical variant available at the time as well. So Core AVI is very interested in seeing these standards added to the next version of the FACE technical standard. We think for what I mentioned before, when we're talking about reusable portable systems, these standards align directly with that when we're talking about using hardware like FPGAs and GPUs for more than just graphics, for compute systems as well and vision systems. So this is something that we want to see added to the next version of the FACE technical standard, and it's something Core AVI is working towards. From the visualization perspective, as Matt mentioned, ARINC 661, which and OpenGL already called out in the FACE technical standard. And so from the visualization perspective, that already fits in with the FACE technical standard.
So I will make a little comment just to back Lucas on that one. The actual 3D objects that are now part of the ARINC standard are not part of FACE yet, so we would hope it would appear in there in the future.
It was actually at the most recent FACE technical working group for graphics, and the issue of Vulkan was raised, and the possibility of putting Vulkan SC into the standard was discussed. There's a lot of interest in doing that. So there are discussions going on about how we would do that and what time scale. So that seems to be moving forward. Next question was, when augmenting the real world with imagery derived from synthetic data, how do you ensure that the synthetic representation is consistent with the real world? What validation is necessary for the synthetic databases to ensure they accurately represent the real world? Seems more like a certification of data question.
I was going to say that. So some of it is, as you mentioned, Paul, there is a challenge when you've got these synthetic views, is how good is that data? How was it validated? Where did it come from? How up to date it is? So obviously with any type of data, it can be kind of low fidelity, low value. And then there's a usage of what are you going to use it for on there. So you have a question about what's that data being used for. Typically, and I think it comes back to the EVS question, is if you've got an enhanced vision system like some of the head-up displays currently today, they do have 3D databases, and what do you do, and what's the situation for the correlation? So some of the systems actually say we have a synthetic vision, and then we use other sensors and we superimpose them, and it's up to the pilot to say, well, that looks like a complete mismatch here, there's something misaligned. That does leave the onus somewhat on the pilot in that respect. There are obviously, if you're looking at the short range, you've got your LiDAR, you've got other kind of vision systems that try and do correlation. So if you're trying to process, you could have a database and try and correlate with what your sensors are seeing and kind of flag to the user that there seems to be mismatches either with LiDAR data or the vision system doesn't seem to be matching what the kind of synthetic view is as well. So there's various approaches you can take on that, but a lot of it comes, what are you using it for? What's that data? How good was it when it was collected? And I think there's a lot of discussion about when you create these databases, how do you ensure how good they are and what's the source of them? And obviously you don't want corruption on them as well. So kind of ensuring when you upload them, there isn't problems with that data. So it is a problem. There's obviously some methods to kind of take an approach to check the correlation and check the approach. Some of the ones rely on the pilot to do that checking. There are other ways that you can try and do that with a kind of computation of taking different feeds and trying to ensure that there isn't errors or mismatch going on. I don't know if you've got any comments on that, Lucas.
I think you basically covered the same type of points I'd want to talk about, where again, it really depends on the application and the correlation and making sure, sorry, that ensuring that the data is reliable is the same as any type of sensor that well, the idea is the same as any type of sensor on the aircraft today that you're using. You need to make sure that data source is reliable. It's no different if you're capturing it LiDAR or like altitude information or something like that. Yeah, I think you covered all the points I would have wanted to talk about.
I'll add a couple of quick things. One is that in the systems that I've seen actually deployed like this, they always make the useful recommendation that the pilot not actually rely on the information that you can see on the screen, which always seems to me to be a bit of a cop-out, but such is life. The other thing is that one of the applications that Prosagus was involved in, which was a degraded visual environment application, a lot of these are more military oriented rather than commercial applications, although there is obviously clear application in both areas. And the way that was done in that case was to use a mix of database information and LiDAR in order to check that features that were identified in the databases were actually physically there, or vice versa. We're getting down to the last couple of questions, so for those of you who are still listening, we will be done in a few minutes. The next question was, you seem to have a root certification for the engine to accelerate a deployed neural network, but how do you see the certification of a neural network application itself being achieved?
Okay, so I think that's a question more towards myself, but it's a very interesting question, and it's still, I would say, an open question within the industry. A lot of research is being done on how you can actually prove the intent of the neural network, or train it in such a way that you can be confident that what it's giving to you is reliable or trustworthy, or if the neural network itself is unsure about the result, it's notifying the system that it's unsure about the result and that maybe it shouldn't trust this result. And so that's still something that's being actively researched. When we're talking about certification of a neural network algorithm itself as well, it's important to distinguish what level of certification, like what is the task that we're trying to use the neural network for? Is it okay if there's a certain amount of uncertainty associated with the neural network? So that's kind of my answer there. It depends on what you're actually intending to use the neural network for, and again, to follow whatever the most up-to-date current research is showing for how to give guarantees about your neural network when you're training it, when you're developing it, and making sure that the data sets that you're using are diverse enough that there isn't going to be issues where it's showing something that doesn't exist. For example, if you're trying to detect plane in the sky, you need to also train it to detect something else in the sky, or the fact that there is not a plane in the sky, so that it can't be, it's not searching to find a cloud that looks like a plane in the sky or something like that. That you need to think of these edge cases from the training perspective as well.
Yeah, there's actually a follow-up question to this, which is related to that, Lucas. How do you collect data to train neural network models for aviation? Are you aware of simulators that would render sufficiently realistic data so that this could be used for generating training data sets? I will actually give a partial answer to that, in that Prasagius is involved in some projects related to this by providing simulators that we believe are sufficiently accurate to do that. Sorry, Lucas.
That's okay. I didn't realize you're going to answer there, Paul, so I apologize for speaking over you.
Editorial comment.
Yeah. So in terms of the actual training data, Prasagius, yes, they provide simulated data. There are companies out there that exist who have large swaths of data that they've captured from different systems, not mainly focused on aviation, just in general, that they sell their data and you can get access to. I would also encourage, if you're developing a specific neural network application, I would say it's important that you understand the data that you need, and you're doing some data capture yourself. You as the application developer have the best understanding of how you actually want to deploy this. So having an idea of the data that you want and actually capturing reference samples of data yourself is very important.
All right, thanks, Lucas. So the very last question, which appears to be a repeat question, so I'll answer it myself, is that in the next presentation, will you be talking about head tracking systems? And the answer is yes, we will. All right, I'd like to say thank you very much to everybody, especially all of the people who stayed longer than the time originally allotted. Still a bunch of people online. Thank you very much for hanging in there. All the questions that you've asked, which I found quite interesting. So we hope that you found this webinar interesting and useful, and we look forward to the second one. Thanks very much. Please fill the survey in when you leave. Thank you. Bye-bye.